Very exciting. This is our first, I don't remember when we've actually had a joint colloquium with the Institute of Optics, along with the local chapter of the organization formerly known as OSA. But it's great to have everybody here. What we've done for this one, because our normal colloquium is at 3:30, we've moved it a little bit later. Of course, it's a little bit earlier compared to what is usually done with the local meetings, but we thought it would be a great chance to get the two communities together. And for added incentives, at least for the students and hopefully for the rest of you, we do have food afterwards. So if you didn't sign up for that, we may be able to fit you in anyway. I'm Tom Brown. I'm director of the Institute of Optics. And apart from passing the chairmanship here on to our house chair, Kyle Kafka, the only other thing I'd like to say is that any member of our community is welcome to attend our colloquium. They are here at 3:30. If you'd like to be on our colloquium list, you can let me know or let Kai Davies know, and we'll be happy to add you to the list. You just have to listen to the half-hour timeshare pitch. No, actually, we don't do a timeshare pitch. What we do is do an industrial associates pitch and tell you why, if you're from a local company, you really, really, really want to be a member of the industrial associates of the Institute of Optics. But with that pitch passed, I want to pass it over to Kyle Kafka, who's house co-chair and helps organize this series.
Thanks, Scott. All right, so hi, welcome everyone. Thanks, Tom, for the introduction. I'm Vincent Tagliamonte. I'm the Optica program chair for this season of talks. And it's been a pleasure to try and put together this first, I think, as Tom mentioned, joint colloquia here. So we really try and find ways to bring the community together as much as we can. And we've been hosting these series of speaker talks for Optica. They're typically on Tuesday evenings. For the joint session here, we wanted to kind of open it up to students. We wanted to have it work with the schedules, so we've adjusted that time at least for this talk. So it's been nice to be able to pull that together to increase the collaboration between Optica and the Institute of Optics here. Hopefully this will be the first of any of these kinds of series of talks where we have a joint effort. So as the program chair, I usually just like to kind of mention some of the upcoming events we have, why we host these events, why we think they're important. So just starting with that, the events are really focused on the Rochester area, optics and photonics, for companies, for students, for professionals in the area, to kind of spread awareness as well as increase the collaboration in the area in the optics and photonics industries. So many students here today may not realize that, probably as you're in this area, but Rochester is quite a unique hub for optics and photonics and has been for many decades with a rich history in optics. And as such, there are a lot of companies in the area that support optics and photonics work. So we try and have speakers come from companies. We also encourage speakers to come who are students, people who are professors or faculty at universities, and any of the supporting industries in the area. And so the goal is really to just kind of bring people together in person. We have been trying to do that this last year or two after several years of COVID, where we maybe didn't have as many talks or we had some Zoom talks. So we're really trying to get back to working in person, being together, having the chance to maybe meet new people, network a little bit, and get to know a little bit more about what's going on in the area as far as optics. So that's kind of the overall mission here. And to do that, we really rely on the support of corporate sponsors. So we had our slides up earlier thanking our corporate sponsors in the area. If you'd like to become a corporate sponsor, you can talk to myself or Kyle, and we can give you information about how to do that. Of course, along with that comes some perks and privileges. If you like to schedule talks that tell more about your company, you're welcome to do that. We can also kind of arrange talks that are a little of both, where maybe you're talking on some technical points, or maybe you're talking because you're looking for students who may be graduating and you're looking for new employees. So that's a good opportunity for that as well. So thanks for our corporate sponsors for helping with that. The speaker tonight is Dr. Ju Wang from Corning Research and Development Corporation. It's been a real pleasure getting to know Ju a little bit these last couple of years. He's very enthusiastic about helping to bring this collaboration together. And he's actually already given a talk for us in the fall as part of just Optica. But he says, I have many, many talks. I have lots of interesting things to talk about, so I'd be happy to come back. Of course, we took him up on that. So here he is again for you this evening. It was a great turnout last time. Ju gave a talk at the Luminate facility, and we had a really nice talk and discussion with lots of people there. So this is, I think, a great way to start this joint seminar here between Optica and the Institute of Optics. So a little bit about Ju before we get started. So again, he is with Corning Research and Development and is an SPIE fellow with the Corning Advanced Optics. And he's a senior development associate at Corning Advanced Optics, as well as being a fellow. This is in 2023, SPI fellow. So he's strongly interested in light matter interactions. He pursues fundamental understanding and has a strong interest in cherishing this industrial technological innovation for laser optics, precision optics, and development of optics and photonics in the area. So prior to joining Corning, he was a professor of physics at Tongji University. He was a German Volkswagen DAAD research fellow at Würzburg University, and he received his BS and PhD degrees in physics and optics from Fudan University and SITP CAS. So that's just a very brief introduction to the speaker. Of course, as an SPIE fellow, Ju has had a long and illustrious career in the field of optics and photonics and is widely recognized as an expert in this field. It's very fortunate he's here in the area at Corning, so it's a real pleasure for me to introduce him tonight. And his talk will be on laser-induced damage of dielectric-enhanced mirrors at 1064 nanometers. So with that, thank you all for coming. Please have some coffee, enjoy the talk, and let's welcome Ju for tonight.
So thank you very much, Link, for your introduction. Really my pleasure being here. I'm used to come on the seminar, from the back door after work or left early before COVID. So I feel kind of honored to be here, and also sense special connection between where I work and the institution, right? And the on Fairport or advanced optics, in Fairport, this should be prepared, right? And so some of my colleagues here, it was found by the faculties at the institute 70 years ago. It's hard to imagine, right? The commercialization at that early age, early years. And so in Fairport, we have, multiple conference room named after different people. And the largest one, I think, is the Hopkins, right? So, basically, my coworker also contributes, that will interesting story between the connection and the institute and the early days, and towards correct all the work in this community. And so what we are doing, basically we are continue inspired by the optics and the optics in engineering. So this just a couple of our recent publication actually happened to be in optical engineer. That's SPIE peer reviewed journal. So the topic including UAV optical glass and testing by these optics basically forming optical chips by UV and UV wavelengths. And we also we had to go through multiple innovation. So this is basically a corrosion resistance, anti-refractive coating for zinc selenide, zinc sulfide window, and it's been used for infrared, sensing and night vision applications. And one of the actually is the F-35, the latest, flight jet, one of the application. And so, after Vince talked to me, I said, well, how should I organize? Corning Advanced Optics has a very broad, coverage, right? And from, semiconductor industry to mobile consumer electronics to aerospace defense. I think, well, probably I can only talk about what I personally be involved or enjoy doing, and also try to select, the paper or the public presentation we have shared with the community. And then by doing that, it's easier to get, since within industry, we need to make sure, to get approval when we present things with the community. The good things, I cite the correct reference. So make sure, it's follow the policies, right? So yeah, I also try to extend that portion in the introduction, basically, to share with the specialist students what we are doing in, optical engineering, right? And then we focus a little bit about the laser damage, the fundamental understanding and the what do we learn, how we do, and why we do those, optical engineering, right? And then give a summary. So, yeah, first of all, I'm assuming everyone know what is the EUV, right? The EUV has been used extensively, for just semiconductor lithography, chip manufacturing, and they represent 13.5 nanometer in wavelength. And so it's the most advanced technology. And maybe, you have the product in your pocket, like the iPhone, A15 chips actually are made by using EUV and with a 5 nanometer, the structure. This is just a diagram of the chip manufacturing for EUV. In EUV, no material is transparent, so we have to using refractive optics. So, and all these optics are mirror-based, so we can take a look. We spend some time actually analysis here, and in the past year, we try to understand how to characterize EUV mirror, what's the EUV, how to design, basically step into EUV business, right? So this is a TM image on the upper right. So you see, for the periods, moly silicon periodic structure to get a higher reflectivity at 13.5. Each individual layer only 3 nanometer and 5 nanometer. So the challenge is the maximum, the best reflectivity around 70%. So what's the rest, where the rest of light, go? Basically, it's thermally, specifically in the system. Right? So that's why it requires ultra low expansion costs as a substrate. And also, that's why we spend the time to understand the thermal property of the glass material at the different, operation temperature. So that's the paper published last year, I think. Then step up the VUB. That's the next generation for inspection system. Since when the feature is smaller, you want to use shorter wavelengths, right? The current, basically you can use for inspection. So the next generation is broadband, 120 nanometer to 190 nanometer using laser sustained plasma source. And in this case, the optics still need a reflector. So if you look at upright, the different material, right? So the aluminum gives the best reflectivity at a shorter wavelength. And then if we expand that to, the desired wavelength range on the left side, so from 120 to 190, aluminum gives, close to 90% reflectivity as a mirror for optics. But one challenge is the degradation due to surface oxidation. So aluminum is easy to be oxidized. As soon as it's formed a couple of nanometer native oxide, it's protected, right? But what are we going to do? So we, have a program basically try to find a solution. We are using atomic layer etching in situ to remove the 3 nanometer native oxide, and then using atomic layer deposition fluoride to protect the aluminum mirror. That's still ongoing work, but our team at the Student Park, we present here some result last year at the atomic layer conferences. And now further step into DUV, right? So DUV in this case represent 193 using excimer laser, right? And so calcium fluoride becomes the material of choice for 193 laser optics. Because of the wide band gap, when electron volts, 103 nanometer correspond to 6.4 eV. I still remember the conversion when I was a college student. My professor, told us, if you remember this, between the conversion between energy, photon energy, and the wavelength, it will be benefit you, in the long run if you are in the optics, right? So I frequent the back and forth. And so actually calling those calcium fluoride in advanced optics, Canton, New York, it's close to 1,000 area, where they also make UALE ultra low expansion cluster over there and the high purity silica for lithography for semiconductor inspection system. One of our optical lens designer is also here with us. And so now, we have been working continuously to improve the laser optics performance, and I try to figure out, what's the best way to determine the, improve the performance of the laser optics. And so, one side basically, we can get information from field return or the, use case lifetime. And then we can also, we conduct ALDT, so-called accelerated laser damage testing internally and work with our customer. And then, we also conduct a laser-induced damage threshold test. So Jerry is here, my coworker, alumni of the institute. And this on the right is an example of the laser-induced damage threshold test. Basically, it's an instant test, right? We try to figure out, okay, with such a quick test, what we can learn compared to, the ALDT or use case or field return. We try to make, some connection. And we also share this, actually this work joint presented with one of our customer, Simon from ASML. And so speaking calcium fluoride, it's a fun crystal material to work with. In addition to laser, testing, we also try to find other alternative way. Here is an example. We use X-ray, but high photon energy with a loading X-ray emission. We evaded the crystal to understand with regard to one, it's kind of the color formation is related to the surface quality. With different surface polish quality, as you improve, you can see less coloration or defect formation on the X-ray irradiation. And then we also develop, like laser durable grade calcium fluoride. So we use a similar technique and, apply our so-called subsurface damage-free surface finishing. We compare optical grade on the left to the laser durable grade with 3 hours X-ray. By comparison, you can see the durability, it's kind of improvement, right? So we thought that, and also we conduct, XRD rocking curve to compare. Basically the concept is if the crystal is better, we should get a narrower for with half maximum at the X-ray diffraction peak position. Right? So these basically you see the optical engineering is kind of material science and characterization, physics. It's a combined chemistry. It's a combination. Right? So in addition to those, we as part of our precision optics, we do make compact optical system. Here is an example. We presented this in 2018. Basically, it's a 4-channel fluorescence imager for human genome sequence. So with this, you see the complexity of the whole system, right? I don't know how many of our lens designers are alumni of the institute, but most of them are. And this is, the compacted system, and we, using broadband and anti-refractive coating, try to cover, different refractive index, or different type of optical glass, and take care of the, surface curvature, things like that. And the low light show the pupil uniformity at a different wavelengths. What we expect for this objective lens. So this is another just an example to show the what we do in precision optics. Right. So Corning has mobile consumer electronics business, and the Gorilla Glass as a cover glass for display is well known. Right? So we, years ago we helped, we using develop a resistant anti-refractive coatings, and actually using silicon, take advantage of silicon nitride. We know silicon nitride is very hard material, right? So using just the silicon target, uses sputtering process by changing the gas ratio between oxygen and the nitrogen. We can tune the refractive index from, the glass silica to silicon nitride. So basically, use one target, we can, change the layer fit hardness as well, right? Based on that, with multi-layer project, we can design anti-refractive coating, but also, increase the surface kind of scratch resistance. So that they are, over the years, several products announced associated with this approach. So now another thing, another AR, actually here is, I think a dominant. We used to call anti-refractive coating AR, but now augmented reality is also AR. This AR basically require, a high refractive index to, there are many advantages. So Corning to make index higher, greater than 2 for this application. But as the index increase, we know the reflection also increase. For the single surface, we can, for glass, typically it's 4%, this make up to 10%. So we do need a kind of anti-refractive coating. We call it ARC, right? This basically is a grating, on one side, another is, outermost surface, put the AR coating. So now the question, can we put regular, broadband AR coating there? it turns out, this drawing actually, is incorrect, right? And so since the total internal refraction actually occur at the outermost surface, so that means the anti-reflective coating needed to have extremely low absorption. Otherwise, the multiple is not the normal. Let's say you have 0.2% at normal view, but in the waveguide mode, the beam is going to bounce around many times. So that requires extremely low absorption broadband AR coating. So we work with facility in China where they make the product, develop low loss AR coating for this application. Now we step into longer wavelengths, in the IR, right? And where Corning has advanced optics has a facility in Key, New Hampshire. They specialize diamond turning optics for aerospace defense application. And here is an example. Corning is making hyperspectral, imaging, and sensing. In this case, using diamond turning of that substrate. And silver is one of the material of choice. So we develop it using ion beam assisted deposition to make fancy name, enhanced durable innovative silver mirror, basically to cover this for this application. And now we step into the laser damage of 1064. This is the, we have been making this product many years, more than 10 years. So over the years, so we, through optical engineering, we try to, have better understanding. So basically, this is, just a two mirror and expand multiple wavelengths, and it also has the capability to improve or enhance the signal to noise ratio in sensing in the middle wave IR. And there are a couple of requirements. And here I just highlight a low near angle scattering because the beam path length, right, to the to the long distance target. And another is laser-induced damage, the 1064. What we work with actually Fraunhofer Institute in Germany, Vienna. That's another optical valley or center in Germany, right? Similar to Rochester in the US. So we, determine the angular resolve scatter. One challenge, basically, it's very challenging to determine the near angle of scattering after, less than 2 degrees from the specular beam. So what we did, through literature, through our, we use log scale. On the right, we can predict what's the near angle scatter based on the angle resolve scatter measurement. And then from that, we, basically share with our customer and convince them, basically provide manufacturable specification for us. Now regarding the, multi-band refractivity, I think most students know, optical interference, right? If we have a quarter wave optical multi-layer structure, and then you can get a mirror. So, this is, let's say, this mirror designed for 1064, using similar, set of material, you can just increase the laser, just increase the yeah, sorry for somehow it's instead of one by one. So now we have a chance to back review all the slides I have. So So here we are. Okay. When we stack, let's say, two mirror design together, you can get a dual band, right? But in order to take care of the middle wave, it's kind of, you can use simple encoding. In this case, actually, we're using aluminum as a substrate. The benefit is kind of it take care of that long wavelength. It's significantly reduce the cost, right? For for manufacturing. Yeah. So actually, sorry for the let me back to the slide. Okay, yeah. Yeah, that's yeah. Back to normal. Okay. Yeah, sorry. So by combine, the multi-stack put on the diamond and aluminum substrate surface, basically we can make it multi-band mirror. And also for the middle wave IR, we do not require, thicker coding, things like that. So we basically, regarding film deposition, we use, plasma source to assist them make, for half year, we use reactive deposition to make a densified coating. And so we combine, two electrometer, one from the VUV wavelength region, another, for to the long wave IR. Based on this, we can, generate the optical dispersion for the silica and the half year, and it's the, if when we get the dispersion, and then we can design different mirror, optimize the process, right? So now let's move on to the laser-induced damage. The laser-induced damage, we look at the damage morphology, seems all of them are associated with defects. So we try to understand these defects, associated with our deposition process or cleanliness or environment, right? So what do we do? Yeah, we look, using atomic force microscope to measure, the coated surface and compare to uncoated substrate surface. And we do see some correlation between the uncoated substrates. We do see some submicron, scale defects, and so on the coated surface, it's much bigger. It is up to micrometer scale. Although, we can make products, but the damage threshold, as the damage threshold requirement, increase, we have to figure out how to mitigate the surface, right? And we also using a laser scan microscope. Basically, it's a confocal microscope, which can make a 3D scan to get the depth information, right? So here is an example. You find the two defects, S1 and S2, right? You make a cross section, And then from the image process, you can get the depth information about these two defects. Since these both defects are traced back close to the substrate surface. So to convince ourselves, we start using SEM, scan electron microscope. And first on the left is basically we tilt the substrate to get better surface morphology. Now you can see those defects, right? Like nodules. So we use focus on beam, make a cut. So, some things right start at the interface, let's say the S1, but the S3 seems a little bit away. So we try to figure out, hey, are they, it's kind of, what's the start point, right? So, and also what are those compositions? We start to look at the substrate, and we do see those imperfections because the aluminum alloy is kind of has a composition like, iron chrome, and for mechanical strength purpose. So we use XRD to see, hey, where are these surface imperfection? What's the composition? You can see some chrome, iron presented in those imperfection area. And what do we do? Okay, we find larger nodules, and then to make a cut to determine, hey, what's the composition, right? Anything associated with the substrate material. In this case, actually, we do see the seeds using EDS. You can basically X-ray spectroscopy. You can get the composition information. In this case, we do see that's basically it's magnesium and aluminum, as seeds and tube.
We still only see slide 19 on the Zoom meeting.
So now we learn what we learned over the years from SPI laser damage. It's so we take the similar approach, try to simulate, calculate the damage, help us understanding the damage mechanism. Basically,
hey, excuse me, can you guys hear me?
There are correlation between your seed size and the nodules.
I hear you.
And
yeah, it sounds like they
so
can't.
We also take advantage of the FDTD. Basically, it's a finite difference time domain calculation to simulate the electric field, penetration distribution. Since our current standard, software cannot handle this 3D, so we work, one side with people in Fairport and also at Surin Park, where scientists specialize in modeling, and we were able to establish, 3D modeling to calculate. Here example, on the left is a perfect multilayer structure. On the right is, half micron defect seeds supposed to sit on the substrate surface, and then how the cone forms. This is just a geometric simulation. And then we can see, when you apply, irradiated with N64 nanometer laser, how the field, strengths, distribute. So you can see that actually it's focused deeper into the aluminum substrate.
Apologize for another interruption. Zoom is not catching up with us.
Okay.
Please continue. Sorry for all these interruptions.
So, yeah, and then we compare, it's interesting. You compare this kind of simulation to the actual cross-section damage from, SEM. You see the similarity help us understand why the damage so deep into the subject. That's just part of our learning, our experience. But moving forward, how we can mitigate stuff, right? We do kind of pattern, develop the process. Basically, we use PVD aluminum to mitigate the aluminum alloy and to eliminate those things. Based on that, we can expect, okay, without, for the aluminum alloy itself, the laser-induced damage threshold, we measured a quarter, per square centimeter. And if we apply our, surface modification, we can increase the damage threshold by 10x. And then when we put dielectric layer, 5 periods there, and then you can further increase the damage threshold to 5. And then the more you add, the higher the damage threshold. But one condition we need to make sure, that suppose it's defect 3. If it's defect, because then the thicker the layer you put, and then it still forms the noisy defect. So based on that, we kind of correct, okay, what's the, damage limiting factor at a different, stage or different configuration. So based on that, we can estimate, the laser damage threshold as a function of the stack period on the left, without defects. That's purely due to the hafnium silicon multi-layer stack, right? So up to 9 period, you can get around 100 joule per square centimeter. And then on the right, the process is laser-induced damage threshold as a function of the seed size. That gave us, the larger the seed, basically further reduce the damage threshold, right? So that gave us a sense of where we should control our process, make it manufacturable, how much smaller the seeds or the defects we care about, on the substrate surface. And with that, I think here is a summary, I share some personal adventure with the advanced optics, especially in optical engineering, and try to use that as an introduction or what do we do in advanced optics, right? And then we focus on laser-induced damage of the enhanced mirror to basically just to show how we do the laser damage analysis and how to do some simulation, and then followed by surface mitigation. And these things still kind of can be applied to other even passing fluid laser optics at shorter wavelengths like 493. So the optical engineering process allowed us to basically make better understanding, right, the fundamental, and also help us develop like how to make a cost-effective optics. So that's the part of my presentation. But before, last but not the least, many of my coworkers, over the years, many of them are alumni of the institute, and even the laser damage we did, some more did at the Spike in New Hampshire. And Mike Thomas is also alumni of the institute. And so all these over the years, I've been in Rochester, different years. So this helped me understand why there is a bench optical, Yeah. I remember I see it somewhere. I was impressed. Finally, I found it. Do you know where it is located? Good. Yeah, just behind the entrance, right? The ground floor. So then whenever I saw that, it kind of remind me, wow, we are proud of the community, and proud of the Institute of Optics and the optical local tech contribution to to make a connection. Thank you very much.
So thanks to Ju for the nice talk. I think we have some time for a few questions. We can answer some Zoom questions if there are any. So yeah, please.
So how many periods do you need in your device, in your Bragg mirror you're making? How many periods do you use typically of these two layers you're putting in?
That's good. Yeah. For it depends on how many.
I understand laser damage.
Yeah.
That should depend on that, but reflectivity also depends on that.
Yeah.
So how many do you use typically?
Yes, depends on the band, right? If you make it about need one single band, probably I think 8 to 9 periods, it's good enough.
Yeah.
But when we consider second band, now we have to
reduce that probably. Reduce the number.
We needed to add additional band to take care of that other wavelength.
Right.
So then we have to add more layers, structure, things like that.
Right.
Yeah.
Related to that, you showed that there was a significant increase in damage threshold as you added more periods. It went from like 0.25 to 2.5, and then you started to add the coding, and then it went up to 5 times and 100 times.
Yeah.
Can you go back to that slide?
Yes, that's increase the damage threshold, right? Yes.
Yeah. Quite a significant increase, yeah.
One challenge I try to, okay, I was able to now. Yeah.
Right there.
Yeah.
How does the increase in laser damage threshold correlate to the strength of the electric field at the PVD aluminum interface? Is it directly related?
Answer your question. Simply yes. We did a simulation with a different, configuration, but I did not prepare the slide here because that time consuming, and that's if you're interested,
Sure. I mean, I guess the point there is because when you add the multi-layer coating, you're going to be putting more electric field higher in the interface structure.
Oh, actually, it's more, basically the coating is going to outmost or top layer is going to take more of the field intensity. If, there is no defect.
Yeah.
Yeah.
So what's the absorption mechanism at the defect? Is it usually exciting surface plasmons? What's causing the enhanced absorption that produces the damage when you have a defect?
Oh, yes, that's a good one. Help me, expand this, right? Let's say if we have a perfect defect, basically it's in a simple approach, it's function like optical lens to make the field more focused, right? If you have a, defect-free versus there is a cone shape, and then optically it's function like, focus the beam. If it's the collimated beam, and then it's focused all the way down to the substrate. Yeah, that's the one of the possibility. And then, as soon as the light intensity increase, these seeds actually absorb, right? Absorb that the laser energy, right? In the meantime, because of this shape and the boundary between the cone is relatively weak, so there are kind of a nodule effect ejection as you irradiate. That's also an additional, damage mechanism. Basically, eject and then the laser is going to hit the substrate, without the nodule. So there are a couple of, mechanisms happens maybe simultaneously. Yeah.
Question. I guess my question was: is it a thermal effect or is it a field effect?
I think when you have more layers, it's still the effect. If you have less layers, since the coating hafnium and the silica, they are absorption free in that wavelength. Right? Aluminum, we know it has like the refractive 95%, so 5% absorb. So when you start to add, without the basically, that's why, when you have, how to say, it's a thermal process, I think, with less, enhancement.
Hey, could you go to slide 34?
For pure
Next
aluminum.
If you look at the crystal structure of the damaged area, is it polycrystalline? Is it has any shape, or is it random?
You mean the aluminum?
Or the aluminum or the alloys?
Okay. Yeah, it has a crystal structure. Actually, we did some, X-ray, diffraction. Based on that, since only, crystal structure show those, one of that. Yeah, here, basically, this, you can see the X-ray diffraction. We can see that alloy, invaded with some kind of inclusions. These are, iron mechanism and form actually for improve the mechanical strength of the aluminum. Otherwise, the aluminum is too soft. Doesn't have enough mechanical strength for those, applications. Yeah.
Could you have the same slide 33, if you could go back, please.
Okay.
Great presentation, by the way.
Thank you. Try to find.
So, Joy, with the thicker, the stack at the extreme right-hand side, which you have an LIDT of 100, the defects are typically the nodules. I think you're gonna show those, right?
Yeah.
And the defects on the aluminum itself, are these different defects as compared to the one that you saw with the hafnium silica? Because you've gone from a defect-oriented absorption and back to a defect-oriented failure, right?
Mm-hmm.
So defects at aluminum are significantly different as what you saw on the hafnium silica stack.
I see. Basically, you mean the PVD aluminum?
Just aluminum itself, yeah.
Just the
aluminum, yeah.
Okay, aluminum 661.
Yeah.
Yeah, it has, since in addition to aluminum, the other, inclusions, like they have a much higher absorption than the pure aluminum.
Okay.
And also our PVD process is further smooth, eliminate those kind of bumps, from surface.
Okay. And if you reduce basically the defects with the hafnium silica, is the bound higher potentially for the LIGT?
Yeah, if you reduce those defects, then you can get. I think for certain low defect area, we were able to get a laser-induced damage threshold up like close to 90%, 90 joule per square centimeter. Yeah.
Thank you.
On this aluminum layer or surface, it does not look like a very good optical polish or finish or material. Is it structural material?
Yes. Actually use, in the defense business, they use the structural material not only for the frame, but also for the optics. So
okay.
It's not, our.
So if I understand correctly, this application was to take a structural material and try and put a coating on it so that it is better?
Yeah, it's one side is the cost. Another side is kind of, when you have like a airborne, different environment, it's much stable. You can throw it on the floor. It's still there, right? Everything is kind of, one material. So for glass, mechanical mounting, that, right? That's a challenge. We have to control these thermal, and So the gravity effect, right?
Well, have you considered putting a layer of aluminum on top of your alloy material? Just have a nice optical property.
That's what we do. Yeah, probably I didn't,
I'm sorry, I misunderstood this.
Yeah.
I see.
Basically, that's what our intention. We try to use physical vapor deposition, pure aluminum, and to mitigate the surface, to make it more like, optical surface, and then start from there.
We have some students here also. Any students have any questions they'd like to ask? Good to have your contributions as well, since you all made it. Anyone interested in optical near engineering or coding development? Yeah, please.
Surface roughness. What role would surface roughness play in the absorption of and therefore the laser damage threshold?
Okay. Yes. So it's, we haven't basically established the real kind of surface roughness versus, the laser-induced damage threshold. But the things, one thing keep in mind is, in the near IR, wavelength is longer, so it's relatively insensitive to surface roughness. And the second, basically the damage seems dominated by, thermal process absorption. So the scatter may impact the system performance, like, the throughput or the refractivity more than the damage threshold.
Thank you.
I have a really basic question talking about the Bragg mirrors coatings that you were putting on. If you were to use materials with a greater difference of index of refraction, you could use a single set of layers to make a wider, more broadband mirror, as opposed to having to do two different layers for specific wavelengths to do that. Are you just limited in the materials that you have at that wavelength? Or
Yes, that's a good question. Basically, from optical point of view, right, you can use other material like, for example, silicon, germanium, right? The refractive index 3 and 4, compared to hafnium. So the one reason actually that's also beneficial from the HPRU laser damage, or including the AE and the Livermore. You guys, lots of work for near IR and then to the UV. So the reason we pick this material combination is not only our own capability for deposition, but mainly also related to the understanding of each material limitation. Basically, silica and the hafnium combination is kind of at least one of the best for higher laser-induced damage threshold from the near IR all the way to that's 350 nanometer in that spectrum range. So that's the reason we choose this material. Yeah, for other application, if it's not require higher damage threshold, and it's a good idea to take advantage of larger index difference, right? To reduce the overall complexity of the design or the process, make it all cost reduction. Yeah. Good question. Thanks.
Maybe one last question.
There was a question in the chat. They're asking if you could remind what the pulse duration is of this 64 nanometer laser.
That's a good question. And thanks for reminding me. Basically, we are in the second nanosecond region. It's a 20 nanosecond, the pulse. Yeah.
Okay, thank you.
Yeah.
And this pulse duration can become important for considering thermal effects compared to absorption.
Yes. Yes, and also, the pulse length also impact the damage threshold. Typically, if the pulse is stretched out, then it's more damage resistance, right? The enemy is less, spread out with that time frame. And then, and Livermore, you guys, done lot, the nanosecond, if you step into the picosecond, the femtosecond, that's another damage mechanism completely different. It's going to walk away from the thermal effect. Yes. Yeah, lots of interesting things for the laser-induced damage.
Well, very good. So thank you for all the questions. Please stick around. We'll have a dinner. And thank you again for attending.
Thank you.